phosphates. Thank you. Actually, let me go back and talk about it in the other place first, so that we get a conceptual idea of where we're going. So in trans-ketolase, the reaction is different. Now here, 1, 2, 3, 4, 5, right? Xylulose 5-phosphate, 5-carbon ketone sugar. 1, 2, 3, 4, 5. Ribose 5-phosphate, 5-carbon aldehyde sugar. What we do is we transfer, right? We go from 5 and 5 to 3 and 7. And the 7-carbon one is cetoheptulose 7-phosphate. Right? I'm not going to say, draw ceto, it's not going to happen. So we go from 5 and 5 to 3 and 7. Which means in order to do this, and I've drawn this specifically, so these 5 carbons are these 5 carbons. These 3 carbons are these 3 carbons, which means these 2 carbons have to be these 2 carbons. Right? You see that arrangement? So, somehow we've got to remove this group, which means we have to break this bond, the bond immediately adjacent to the carbonyl, and move just this 2-carbon unit over to this aldehyde, which is going to act as an electrophile. So we've got a slightly different challenge with trans-ketolase. Now with trans-ketolase, we use the trans-ketolase enzyme twice. Right? We use it here, that is 5-carbon ketone sugar, 5-carbon aldehyde sugar, to make 3-carbon aldehyde sugar and 7-carbon ketone sugar. Okay? Later in the pathway, or in a different position in the pathway, it's hard to say later because all this sort of ends up going on at the same time, we take, again, 5-carbon ketone sugar, cellulose, but the 4-carbon aldehyde sugar that is left over from our normal transaldolase reaction. So this enzyme is less specific than we normally think about for enzymes because it can bind a 5-carbon aldehyde sugar or a 4-carbon aldehyde sugar, right, as the target. But again, we're going to go from 5 and 4 to 3 and 6. So we're going to take 2 off the 5-carbon sugar and add them to the 4-carbon sugar to make a 6-carbon sugar. Devin's frowning. Go ahead, ask your question, Devin.
No, I'm back at transaldolase.
Okay. What about transaldolase? What question do you have on transaldolase?
Does it not break the bond adjacent to the carbonyl?
No, it breaks this bond. It breaks the bond on the between alpha and beta.
But the other ones break.
The other ones break on the near side of alpha.
Okay, so it breaks between alpha and beta.
Yeah, this one breaks between alpha and beta, just like aldolase does. Right? Where we expect it. This one breaks at an unusual position between the carbonyl carbon and alpha.
Is that just promoted by the enzyme? For
So now
specify the breaking of the bond.
Yeah. Now, the question is, how do we chemically create that situation? Right. And gee, since a bond making and breaking is involved, what do we suspect is going to be involved? Robbie? Since a bond making or breaking is going to be involved, what do we suspect is going to be involved? What's been involved every time? No, well, an enzyme, but what kind of chemical structure? A carbonyl. Or, when it hasn't been a carbonyl, what has it been? An imine, right? So we have to look for either a carbonyl or an imine being formed in a position that makes this bond the one that will break instead of this one. Does that make sense? Right? We can begin to predict these things. Now let me see if I can find, let's see if I can pull it. Okay, so now we're back to our old friend, thiamine pyrophosphate. Right? Our old friend. When did we deal with thiamine pyrophosphate in the past? In what enzyme did we deal with thiamine pyrophosphate? Say it loud enough that Melanie can hear you.
Pyruvate decarboxylase?
Pyruvate decarboxylase. Yeah. We used thiamine pyrophosphate in pyruvate decarboxylase. And we said that this carbon of thiamine pyrophosphate in the enzyme can be deprotonated. Let me make it bigger. Right? That carbon can be deprotonated. That can be used as a nucleophile to attack the carbonyl, in this case of xylulose 5-phosphate. And when we get that opening and addition, we turn that carbonyl into a hydroxyl. So now that carbonyl is no longer affecting this bond. So by doing that, we make this bond a bond that doesn't want to break. But what else do you see in that structure? Why? What did I say we were looking for? An imine. Do you see an imine-like structure there? Right? The C double bond N right here, right, plays the role of the carbonyl here, which means this now becomes the carbon alpha to it. This becomes the alpha-beta bond, and so now we've moved one over in terms of the bond that we can break. Right? Just this little change, this little use of this coenzyme lets the enzyme system, and therefore the biological system, manipulate which of those two bonds it can break. What's the next 3.5 words that's going to come out of my mouth?
That's pretty slick.
That's pretty slick, yeah. Isn't that slick? That would be an acceptable second answer. Right? That's pretty slick. Sarah's thinking hard over there. Are we good? Right? This is the bond that's going to break. Right? Right now with this carbonyl, this is alpha, this is beta. This is the bond that we would suspect to be the sensitive bond to breaking. By attacking this, creating this imine structure within this coenzyme, that becomes like the carbonyl. That becomes the alpha carbon. That becomes the beta carbon. So now this is the bond that we can break. Does that make sense? And that's exactly what we did before when we used this coenzyme in pyruvate decarboxylase. By doing that, we created a situation where that would stabilize a carbanion when pyruvate decarboxylated to break that bond. Ellen's thinking hard. Question, Ellen? Okay. And so now, right, we get cleavage of this bond, right? This pair of electrons can come back here, which is going to, what they're not showing, it's going to chase this pair of electrons over here, and you get this kind of structure based on the arrows they're showing, right, to keep that carbon from having too many. If you finish their arrows, you're going to end up with this structure. These two carbons attach to the thiamine pyrophosphate. Something deprotonates this. As these two electrons leave, this carbon needs to get electrons from somewhere. if it uses electrons from oxygen to make the double bond, these 3 carbons leave as glyceraldehyde phosphate. And glyceraldehyde phosphate is something, yeah.
3 carbons.
Right, it's a 3-carbon thing that's in glycolysis, right? So if we need to put it into glycolysis, right there we can. Okay? So now we've got these 3 carbons here. If we look at, what?
It's something?
It's something.
That's
It's good to have friends sitting next to you to give you support.
right.
Yeah. So, right, this structure, if we look at the resonance, it has a resonance form where the carbanion is on that carbon. And so now that carbanion can attack the aldehyde of ribose 5-phosphate. Right? That carbanion can attack the carbonyl of ribose 5-phosphate in a typical nucleophilic addition reaction. Right? We get to there, and now if you look, this is the same kind of structure that we had here. Right? We've just added a carbon to it, but it's a hydroxyl attached to this. See the similarity between those 2 structures? There's just an extra carbon there. So now we can just back out of that. That is, instead of breaking this bond, we eliminate this, use the carbanion as a leaving group, get our carbonyl back, and now we have created a ketone sugar 2 carbons longer than our aldehyde sugar was in the first place. Yeah?
I'm not understanding why you would not break the alpha-beta bond now.
You could. And this reaction is freely reversible. So it just depends on what you're using at the time. Then it becomes an equilibrium process. If we're using cetoheptulose 7-phosphate and taking it out of the system by doing other stuff with it, then that equilibrium is pulled this way. If for some reason we have a lot of cetoheptulose 7-phosphate coming in and a lot of glyceraldehyde phosphate, we can push it back the other way. It's freely reversible. She didn't like that answer.
I just don't understand why the first time that we made this intermediate,
We broke that bond.
we broke the bond alpha and beta to the amine, right? And now we're breaking the... Oh, I see.
Right?
Okay.
This is equivalent to that.
Okay.
Right? And the enzyme treats them both the same. Right? And so in the end, where'd it go? This is equivalent to the enzyme to